Yes, good afternoon to all.
Good afternoon, sir.
Yes, good afternoon. Now we'll continue our discussion from here, the program status register instructions. Now to modify the CPSR or PSR register, so we make use of these instructions. So the MRS is the instruction which we use in order to read the CPSR and SPSR registers. Okay. So this CPSR and SPSR register data can be read by using MRS instruction to a register, to a general purpose registers. And similarly, this MSR instruction, observe this, and this is MSR. Okay, so this MSR instruction is used to copy the content of a register, general purpose register, into CPSR or PSR register. Okay, so now this is using this, you can go for reading the content of CPSR or SPSR register. Now using this instruction MSR, you can go for reading the writing the content of a general purpose register into CPSR. In general, MRS instruction is used for reading the CPSR or SPSR register, and MSR instruction is used for writing CPSR or SPSR register. Okay, and that is what is mentioned in the last point. Together, these instructions are used to read and write the CPSR or SPSR registers. So, and one of these two instruction we used in the previous classes when I was explaining the concept of pipelining. So in one slide, it was mentioned, I don't remember exactly whether it was MRS mentioned or MSR mentioned. So, but one of these two was already mentioned. I had told you earlier also that, so this is the instruction which is used for reading or modifying the CPSR or SPSR register. Did you understand MSR and MRS?
Yes, sir.
Okay. So now the syntax of MRS and MSR instruction. Now let us go here. So it is also possible for you to specify the combination of these things. So within the CPSR register and SPSR register that we have already discussed in detail, we have many fields. We have 4 fields. One is the control field, extension field, the status field, and the conditional flag field. Now here, so it is possible for, say for example, I need to update or write only the control field and the others I need not do anything. So then you can go for updating only the control field. Similarly, I want only the conditional flags to be updated. Then you can go for updating this. Okay, by using this MSR instruction. Now here, see here, MSR. Can you just tell me what you can do using MSR instruction? Whether you can read from the CPSR or SPSR register, or whether you can write to the CPSR or SPSR register using MRS instruction. What is that you perform? What is that we do? Please. Yes. Please unmute and talk. What is that I told here? MRS instruction for what? Am I audible?
Yes, sir.
Yes, sir.
See, please speak. Why? See, if you're not speaking, then I can go for muting all of you. So what for I have given the permission for you to unmute and talk. See, whenever I ask something, please do respond immediately. Otherwise, there is no need for me to keep all of you in the unmute mode. So I can just mute everyone and I can talk myself, and then finally at in the 5 minutes or 10 minutes, I can go for taking the questions from you. No, I don't want. I want you people to interact with me. So whenever I have something, immediately just take the mouse pointer, unmute and say yes or no. So don't make me to again look into whether I'm in the muted mode or whether you people are there or left the meeting. Now, what MSR instruction does?
It transfers the data of the CPSR register to another register.
Another register. So this is my destination register. What I'm trying to do now is I'm trying to copy either the content of CPSR or SPSR register into my destination register RD. So I'm trying to read. Okay. Now, how do I remember MRS is for, see, R is there, right? So the first R, MR. So read it. And this S is for setting. Okay, setting. Now MSR. So what we do? See, this is my, again, for MRS or MSR, you can go for embedding a condition also. Okay, so optional condition is also there. Now, so you can see. So we go for writing CPSR or SPSR register. So there is an underscore here. So this can be CPSR or SPSR, and after this there is an underscore. Now after underscore, we have something called as fields. Now this field can be either C, X, S, or F, or it could be all of those things. Okay, so I say I want to update everything in the MSR register inside the CPSR register. So then I write C here, C, X, S, F. No, I don't. I just want to update only the control field. So I underscore CL write. And where is the data? So it is in the register RM. Okay, so the data which is there in the register RM, I'll try to write it into the corresponding field of either CPSR or SPSR register. Hope you people are following. So what if I want to update the control field and the extension field? I'll be writing CX here. So if I want to update everything, CXSF. Now I want to update only the status flags. I'll be writing only S here. Hope you people are following.
Yes, sir.
Yes, sir.
Okay. Now, again, in the next statement, so instead of having the data to be written into the CPSR or SPSR in the register RM, so you can also have it as an immediate number. Okay, and for your reference, the CPSR register is shown over here. So this is the field F, flags, and this is the field S, that is the status, and this is the field X, that is extension, and this is the field C, control. Okay, so you can go for, say, if you want to update only these things, then in the field here you specify only F. Okay, next. And all these things you know clearly. So we have in detail discussed all the fields of this CPSR register. Let us not again focus on those things. Now MRS register. So the high level statement is written. What it does. So this program status register, either CPSR or SPSR, gets loaded into the register RD. Now what MSR is doing, see the content which is available in RM, it is going to update the corresponding field. And this field we specify either by writing C, F, X, or C is for control, X is for extension, S for status, and C for control, and one more F for flags. Okay, so you can, and similarly, so MRS, instead of having the data in the register, so it can also be given in the form of an immediate field. So now here we have an example on the same. So you can just see here. So I'm assuming the content of my CPSR register. My CPSR register initially it is something like this, and by looking into this you can say now, so N, Z, C, V, Q, all these things are in lowercase. That means they are in the clear state. I and F are in the set state, and thumb state is also in the clear state, and this SVC is indicating it as in the, so your microcontroller is in the supervisory state. Now since I and F are set, so what does it mean? So both the slow interrupts and the fast interrupts are disabled. So hope people are able to understand.
Yes, sir.
Okay, now, so what I'm trying to do here, using MRS instruction, I'm trying to read the content of the CPSR register. I'm loading it into the register R1. Next, now using BIC, I guess all of you remember this BIC instruction, bit clear instruction. Yes or no?
Yes.
Okay, so a bit clear instruction. Now my intention is to enable the slow interrupts. I want to enable the slow interrupt. To enable the slow interrupt, what is that I need to do? I need to clear this bit. This bit is 1 right now. I need to make this bit as 0. Okay. Now what I'm doing, I've copied the entire CPSR register into the R1. Now R1, okay, I'm doing BIC instruction, bit clear instruction with this data. What is the data I've taken now? 80. So this is 8. 1 0 0 0 till here 8. And 1 0 is missing here. Sorry, 1 2 3. There one more. There has to be one more 0. So this is the correction. Now this is 0 and this is 8. Hope you people are following. Now why I have taken 1 at this position itself? See, this 1 is at position what? 7th position. So because where is my slow interrupt? Slow interrupt bit number is what? 7. So from 0 it is at 7. Okay, the slow interrupt bit number is 7. Now exactly at that position I have taken the 1. So you can count from here: 0 1 2 3 4 5 6 7, because my intention is to clear this bit right now. That is the reason I'm using bit clear instruction. Now MSR, see, CPSR underscore C I'm writing. Why I'm writing? Can you just tell me what is this underscore C is?
Only the control data.
Yes, I need to update only the control field. So only this part I need to update, and the rest all I need not modify this. This part I need not modify. I want to modify only this part. Okay, so that is what is it. So CPSR underscore C, and my data is there in register R1. What it is going to do? See, the slow interrupt is enabled. So that means earlier it was 1. So the 7th bit in the control flag control field was 1. Now after my MSR instruction is executed, my slow interrupt is enabled. And this is the kind of example which was already shown to you people in the earlier in one of my slide when I was explaining the concept of pipelining. So I guess you people are able to recall that. How many of you are able to recall it? So that pipe, it was in the form of an execution diagram of the pipeline. So do you people remember that?
Yes, sir.
Okay. So, and this is the explanation for the same. I guess you people understood this example. So MSR first copies the CPSR into the register R1, the first statement, and BIC instructions clears the bit 7th bit of the register R1, and then we are copying back the content of the register R1 to the CPSR register, and which enables the IRQ interrupts. That slow interrupts are enabled, and this code preserves all other register settings in the CPSR. That means, what is the meaning of it? So it affects only this control flags, and all other flags inside the CPSR register are preserved, because we are focusing only on updating the control field. And then, and this is an example for the supervisory mode. By just looking into this CPSR status underscore SVC, you can know that. So this is your microcontroller is operating in the supervisory mode. Okay. Next is coprocessor instructions. Next is coprocessor instructions. Now, earlier classes, we understood core extensions. So in the second chapter, I think at the end of the chapter 2, we understood something called as core extension. Do you people remember that?
Yes, sir.
Yeah, what are core extensions? So additional components that surrounds the ARM core are called as the core extensions. And you can also call them as the assistants. So because these things are going to assist the main core in order to increase the throughput. Okay. And then we understood 3 main core extension. One was cache memory and tightly coupled memories. Another one as memory protection unit, and one more is coprocessors. So these were the 3 core extensions, main 3 core extensions that we understood at the end of the chapter 2. So now, and coprocessor was one among them. Now what coprocessor will do? Coprocessors will relieve the burden on the main core processor. So you can have co-processors in the form of IO processors, graphic processors, and all these things. Now, what we are going to understand here is how do I make a co-processor perform the execution of an instruction. So till now, you understood how the ARM core performs the execution of the instruction. How the ARM core performs the execution of the instruction, that is what you understood. So now here, so very a short discussion. It's not a lengthy discussion. It's a very short discussion. It's like how to make a coprocessor perform the execution of an instruction. Okay, so people are able to understand. Now all the instructions what we wrote now, add instruction, multiply instruction, any instruction it might be, and all the programs what we wrote now, so they were the programs or the instructions which were written to perform the execution on the main core. Now what you're going to learn is how do I write an instruction, and I don't want that instruction to be executed on the main core. Instead, I want the instructions to be executed on the coprocessor. Okay, now that is what you learn. So did you got it?
Yes, sir.
Yes, sir.
So now the coprocessor instructions are used to extend the instruction set, and a coprocessor provides the additional computation capability. And this, and again, so the coprocessor instruction, you can have data processing instructions also for the coprocessor. For the coprocessor, you can write the data processing instruction. What are the data processing instruction? We understood move, the add, subtract, all these things. They come under the data processing. And similarly, for a coprocessor also, you can go for writing all these instructions. So you can write the register transfer instruction, memory transfer instruction, even load and store also you can write for the coprocessor. So all these types of instructions, even they can be written for the coprocessor, but till now you understood it only for the main processor or the ARM core. Now we are going to understand how do I write the data processing instruction for the coprocessor and perform the execution of the data processing or register transfer or memory transfer instructions on the coprocessor. Okay, so we discussed only a short overview. That is what I'm saying. So we are not going to have in detailed or the complete discussion on the coprocessor instructions. So it is only a short. It's something like a bird's view. Okay, that is what we are going to have now. So note that these instructions are only used by the cores with a coprocessor. So if I say I have an ARM core which doesn't have the coprocessor, then you cannot write. So it can be, this instruction can be written only for the cores which are having the coprocessors. Okay, next. So let us come now. Now we'll try to understand the coprocessor instruction syntax. So I want to write an instruction for execution on some coprocessor. What is the syntax? How it goes? So it goes something like this. See, CDP. So it's nothing but coprocessor data processing instruction. Okay. Now, so CDP stands for coprocessor data processing instruction. See, you can have an optional condition also, just as we understood for the main core processor. So for majority of the instruction, you can go for embedding the condition. Similarly, even for the instruction that you're performing the execution on a coprocessor, it is possible for you to embed the condition. Okay. Now, what CDP stands for?
Coprocessor data processing.
Yes. So coprocessor data processing instruction. See, it is here. Okay, so performs an operation where not in the main core, it performs the operation in the coprocessor, so which is an assistant to the main core. Okay, next CP. CP is the coprocessor number. It's the coprocessor number. See, it's not like you have only one coprocessor. So you can have many such coprocessors. Now, what is the maximum number of coprocessors that a processor can have? So it can have up to 15 coprocessors. And so the first coprocessor is numbered as P0. So just as we have numbered the registers R0 to R15, similarly, the coprocessors are also numbered from P0 to P15. So it is the coprocessor number. You got to specify. So where this coprocessor data processing instruction which you're writing now to be executed, whether you require the execution of this instruction on the coprocessor 1 or on the coprocessor 2 or on the coprocessor 3. Okay, so this is the coprocessor number. and this is the opcode of the instruction. Say I want to perform data processing, can be move instruction, addition instruction, multiply instruction, subtract instruction, it can be anyone. So this is what we specify. I'm saying coprocessor data. Now by looking into this, your compiler or assembler will understand that, oh, this is the instruction not to be executed on the ARM core. This is the instruction which needs to be executed on a coprocessor. By looking into this, your translator or the assembler will understand. So this instruction has to be executed on the coprocessor, not on the main core. And then, so by looking at this parameter, the translator also understands that, oh, this particular instruction has to be executed on so specific coprocessor. And this is, and looking at this opcode, it understand, oh, this is the kind of operation I need to perform on this coprocessor. And we have, this is the destination register. Now in the when we were discussing writing the instructions whose execution was required on the the main core, we used to write it as RD. RD stands for the destination register in case of the main core. But how do I represent the destination register of a coprocessor? It is CD. CD stands for the destination register of the coprocessor. And what is CN? In the earlier, so I used to write it as RN. What was RN? RN was the first source register within the main core processor. But now it is CN. CN is nothing but the first source register of this particular coprocessor, and CD is the destination register of this particular coprocessor. So even within the coprocessors also there are registers. Okay. Now the convention that we are using in order to access these registers or represent these registers is the C. And similarly, the convention that we used earlier to represent any of the register which is there inside the main ARM core, it was R. So people are able to understand?
Yes, sir.
Okay, so please
Yes,
focus and try to understand. So this is the first source register, and the second one I've written as it as opcode 2. So why? Because so this again, so you can go for performing the pre-processing operation on this. So LSL, shift left, shift right, all those things you can perform. And again, this can be either a second destination register, sorry, source register, or sometimes even it could be an immediate number. So this is the reason, that is the reason we are writing it something like this. So now this is the generalized syntax for any instruction. Generalized syntax for any instruction, any data processing instruction whose execution is required on a coprocessor. Okay, so first you got to specify CDP. Now by looking at the CDP, the translator understands that so this particular instruction has to be executed on the coprocessor. And again the question comes, so there are P0 to 15 coprocessor, on which processor the execution is required. So this will tell. So this is going to tell this is the coprocessor on which this operation has to be performed, and this is the destination register on that particular coprocessor, and this is the first source on that particular coprocessor, and this is the second source on that particular coprocessor. And again, so on this you can go for performing the left shift, right shift, all those things you can perform. Either this could be a register or it could be an immediate number. Okay, so now you understood the syntax of the data processing instruction. So when I say data processing instruction, all the instructions what we understood till now will come here. So logical instructions, arithmetic instructions, move, everything will come there. Next, MCR and MCR. So sorry, MRC and MCR. See in the now. So this two just we now understood. Just now we understood them in the earlier slides. So when I wanted to read the content of the CPSR register to some register, so general purpose register, I was using MRS. Now same thing in case of a coprocessor, it is MRC, and this is MCR. So if I want to write the CPSR register or SPSR register which is there inside the coprocessor, then I make use of MCR. So people are able to understand?
Yes, sir.
And then you can have an optional condition as well here. Specify the number of the coprocessor on which you require the execution of this instruction, and then specify the opcode, so destination, first source, second source, and on the second source, if you would like to perform any other operations like left shift, right shift, all those things you can perform. Next, LDC and STC. So this LDC is something similar to your LDR. So all these days, say if I wanted to load address of some memory location to the register, okay, within the main core processor, then I was using LDR. If the same thing I want to load, if I want to load some register which is there inside the core processor with the content of the memory location, then I make use of LDC. Similarly, if I want to store content of some coprocessor register into the memory, then I make use of STC. STC is similar to your STR. So these two instructions, STR and LDR, operates on your main core, but LDC and STC operates on your coprocessor. Is that fine?
Yes, sir.
There's a lot to understand here in the syntax what I have written. Okay, so now, so this is generalized now everything. So now even if I ask you, can you write some instruction for so the move instruction which needs to be executed? I want the execution of the move instruction on the coprocessor number 5. So very easy. So CDP. So condition, if you want, you can put it and 5, right? So P0 and the 5th coprocessor number is P4. So write P4 here and say move instruction and the content of this to this. That's done. And this is optional. This is optional because for move instruction, we don't require this. So destination register say C0 and the source register say C1. So content of C1 gets moved to this. Okay. So these are the most generalized. These three are the most generalized syntax of writing the data processing instruction, and then reading and writing of your CPSR and SPSR and performing the memory references operation. So that is clear?
Yes, sir.
Okay, and the explanation is also given here. You can see, so coprocessor memory transfer can be done by using this, and CP field represent the coprocessor number, which is usually between P0 to P15. And the opcode here, it specifies the operation to take place on the coprocessor, what operation to take place, whether it is an addition, subtraction, multiplication, division, all these things, whether it is a simple move. And then CN, CM, and CD fields are the described registers within the coprocessor. This is the notation which we use in order to represent the first source. So say for example, C0 is the first source. I write like this, and C1 is the second source, and C2 is the destination, something like this. And so we say you can have available P0 to P15, 16 coprocessors you can have, but the last coprocessor, that is 15, CP15, is reserved for system control purpose. Okay, so it is always reserved for the system control purpose and such memory management. So the write buffer control, cache control, and identification register. Now what it does, so it's going to do the memory management. So write buffer control, cache control, and identification of register. That is the job of this coprocessor. And by doing all this management, it is helping the main core processor. So, but we rarely go for using this coprocessor number 15 to perform the execution of our own instruction. So instead, we go for using the coprocessor P0 to P14 because this P15 has a special purpose. So what is that special purpose is? So system control. What kind of a system control it does? Memory management it does. So it also controls the write buffer, it controls the cache memory, and it also goes for identification of the registers for loading the data appropriately. Okay, so this is the coprocessor instruction syntax. So any doubts in this part?
No, sir.
Okay. Now I have one example. So transferring the content of CP15 coprocessor register C0 to the register R10. So now this is what you got to understand very carefully now. Now what is that we are doing now? C0 is there inside the coprocessor number 15. And where is this R10? R10 is in the main core. R10 is the register which is available on the main core. Now what we are doing, so we're making our coprocessor 15 to communicate with my main core. How? By transferring the data which is available inside its register C0 to the register R10 which is there inside the main core. See how? Say MRC I'm writing, and then P15 is the coprocessor number, and this 0 is the operation opcode. Okay, opcode for transferring the content of my C0 register which is there inside the CP coprocessor to the R10 register. And again in the source and the destination and the first source, I'm writing the same thing, say 0 C0, and this is not applicable for me. I'm writing it as 0. Okay, here CP15 register 0. So the register 0 of the coprocessor 15 contains the processor identification number, and this register is copied into the general purpose register R10 of the main core. Now loading constants, and this is the last slide of the chapter 3. So till now, so you understood how to load a 32-bit address into the register. What we were doing, we were writing it as LDR. Say I have some memory location, and many examples also we have done. So we used to define the value 1, value 2, result, all these things inside. Sometimes inside the code area and sometimes in the data area. If I wanted the address of those things, so this is how I used to write it: LDR RD comma equal to constant. So this constant can be either the variable name, say value 1, value 2. I guess you people are able to recall. And then, so in case if I want to load the address of a label, say sometimes we have written loop 1, correct? No, all these things. Say I want to load the address of this particular loop, so then I make use of ADR. So ADR is so load address. Now what it is going to do, it's going to load the 32-bit relative address of the labels into the destination register. So are you able to understand?
Yes,
Yes,
sir.
sir.
Okay. So that's the end. We are done with the chapter 3 of the module 2. So very lengthy chapter it was, and where today we made it possible, we completed it. So next thing is chapter number 6. This is the second chapter of module 2, writing and optimizing the ARM assembly code. Writing and optimizing the ARM assembly code. Now, till now, you understood the instruction set of the ARM. So how to write the data processing instruction, how to write the memory references instruction, load and store, all these things you have understood. And on top of that, you also understood how to write the instruction for the coprocessors as well. So now what you're going to learn in this chapter is, okay, you understood writing the programs, ARM assembly codes. Now, how do you optimize the code for improving the performance of the computer system? Okay, so always when you're writing the program, we got to write it in such a way that it consumes minimum amount of system resources and runs. Now, if you want to make your program run by consuming the minimum amount of system resources, you got to optimize your code. So you got to make your program efficient. So if you make it efficient, so then it can run by consuming the minimum amount of resources, and that is what we always look to do. Okay, because we never try to write a program which consumes a lot of memory, lot of processor cycle, lot of memory cycles. No, so that is not required for us. What is required for us is writing the program which runs by consuming minimum amount of all these resources, especially when I say ARM. So ARM is the code which runs on the the handheld devices. So most of the devices on which the ARM applications or the ARM programs are running are the mobile devices. So where there are a lot of limitations. We have limitation in terms of computational capabilities, limitation in terms of memory, okay, and limitation in terms of the battery life also. So when you're writing the program, so if you write a program in an optimized way, then the program will ensure that it runs by consuming the minimum resources, and it requires the minimum computing resources. And it also, once I say the minimum computing resources, it also guarantees that so the battery life is increased. Okay, because majority of the handheld devices are battery operated. So for example, our mobile phones itself. So if say I am using a mobile phone and I want to charge it every hour, the frequency of charging is every hour, so then who will use it? Nobody will use it. So the thing is, so if I charge my phone today, at least it should be possible for me to use a single day, one complete day without having to recharge it. So for you to do this, so it all depends on how you're writing an optimized code. So that is what you're going to learn. So now we understand the techniques to optimize the code and make it efficient. So hope you people got the insight into this chapter, why this chapter is all about.
Yes, sir.
Okay. Now, so code optimization. So the first thing I'm starting is why code optimization is required. So it is required for two reasons. One is to reduce the system power consumption. Say, for example, I give you a problem statement and two students are there. So one student write the program for the given problem statement in 10,000 lines. So the another student write the program for the same problem statement in 100 lines. Now you can just compare where is 1000 lines and where is 1100 lines. So 10,000 lines and 100 lines. So it was only 100 lines because he has used his creativity and made the program much more efficient such that it consumes lesser space in the memory. So, and you can just imagine now. So that is what is the optimization. And again, since there are only 100 lines and which is doing the same job as the program which is of length 10,000 lines doing. So you can just, and again, it's going to consume the less power also. Now, how a program with the lesser number of instruction is going to consume less power consumption, because a program with the less number of codes to execute, it requires less processor cycles. And that means the processor is not active for a longer period of time. So it is active for only a shorter period of time to do the computation. So longer the processor is active and performing the computation, it keeps consuming the power. So by optimizing the code, you can go for reducing the power consumption. And you can also go for reducing the clock speed needed. Say if you're writing a very big program, say 10,000 lines of code, 1 lakh lines of code, 2 lakh lines of code, so obviously you should be using a processor with very high clock speed. So these days our laptops and the desktops, they come the processors. So we say they operate at 2 gigahertz speed and 3 gigahertz speed. What is the meaning? So the quartz crystal which is there inside our laptop or the desktop, they're able to oscillate. So 2 giga times, say if I say 2 gigahertz processor it is, so inside that it is the quartz crystal is able to oscillate 2 giga times per second. So that means on every oscillation, it is capable of performing one operation. So, but the mobile devices or the handheld devices, it is not possible for you to have a processor with very high clock speed. So maximum within the mobile devices and the handheld devices. So what you can have is you can have a 16 megahertz. What in terms of mega it is? In terms of megahertz it is. Okay, so 16 megahertz quartz crystal or maximum 64 megahertz quartz crystal. So now if you say I have written a program with too many lines of code, so lakhs of code, then you can just imagine how many clock cycles the processor has to spend. So it keeps spending lots of clock cycles and the execution time also increases and it keeps consuming the power also. Okay, so these are the two main reasons why the code needs to be optimized. Okay, next. And another thing is optimization can turn an infeasible system into the feasible one. So for example, I'm using a mobile device, I have very limited memory. So I have only 500 MB of memory. I have only 500 MB of memory. Okay, so but there is an application which requires 600 MB of memory. So it is not possible for me to run the application which is of 600 MB in my device, because my device maximum memory capacity itself is 500 MB. Now it is not possible for me to run that application. Now if I go for optimization, okay, so instead of making one version of the application, I should be making multiple versions of the application. So one version, say full-fledged version supporting all the features, correct, which is for the devices with the larger memory. And similarly, I should go for optimizing my code and prepare one more version of the application. So lighter version of the application with limited features, which can run on the devices with the limited memory. So now I don't know whether you people are aware. So since you people are very good at the social media, so you might be aware of this thing. So now Facebook comes with a Facebook Lite. So on the mobile, so we don't install the full-fledged Facebook app. So we go for installing a Facebook Lite because that is best suited for the mobile devices and where it consumes small memory and also consumes less processor cycle. Hope people are able to understand what I'm saying.
Yes, sir.
Yeah,
Yes, sir.
that Facebook Lite is an optimized code optimized to run efficiently by consuming limited resources on your phone. Okay, because phone is battery operated, and the Facebook also understands that if the full-fledged app is developed for the mobile phones, it will soon consume a lot of resources and also the power. So now we have the Facebook Lite version. Okay. Now, and another thing is, so it can also make the optimizing the code can also make an uncompetitive system into the competitive one. Say the application, say I'm writing an application. So say if I'm able to optimize the code and produce multiple versions of it, so then it is something like a competitive one. That means that I can have that application running on my desktop, laptop. I can have that application running even on my tab, even on my phone, even on my any other device, portable device, what I have. Okay, that is if you want to make your system or application more competitive, then the code optimization is very much essential. So I guess these points so made you understand the need for the code optimization. Is that clear?
Yes, sir.
Okay. Now, so another important thing for optimizing the code is to maximize the performance. You can maximize the performance. Now, one simple way to maximize the performance of the program is by writing in assembly code. Say, for example, I ask you to write a program for bubble sort. Okay, so one student write the same bubble sort logic using the assembly code, another student writing it using the C programming language, and one more student write it using the Java. Now, same logic they have implemented, but the languages are different. One has implemented it at the assembly code, and one has implemented it using the C programming language, and one has implemented it using the Java code. Now, which one will be running fast when I compare all these three things, or which has the maximum performance? So the code which is written using the assembly code has the maximum performance. So you run all of them. So go for measuring the times. The assembly code, the one which is written in the assembly code, runs much faster than the same program, same logic which is written using C and the Java language. Okay, so the maximum performance can be achieved by using an handwritten assembly code. So why I'm saying handwritten, because assembly code can also be auto-generated. So there are tools using which you can go for auto-generating the assembly code. So but the tools, what they do, they apply the routine activity and then they go for generating the code. So the creativity is not there. See, if I input some design to a tool and any number of times I input the same design and run my tool, what it will do, it will give me the same code. So and it's not like so the first time when I input the design, it gives me a code of 10,000 line, and if I input the same design for the second time, it understands and brings down the length of the code from 10,000 to 9,000. So even 100 times, 10,000 times, if I keep inputting the same design to a tool, it produces the program of 10,000 lines. So instead of that, so if I go for employing and skilled programmer. So first time when I ask him to write the program for some kind of a design, he might write it in 10,000 lines of code, and I'll can the 10,000 lines of code is too much, so and it will not be feasible for the handheld devices. Try to reduce the lines of code. So then he can go for looking into the program, analyze the program, and then again apply his creative skills and bring down the length of the program to 9,000. So from 10,000, he might it is possible for him to reduce it to 9,000. So if still again I say that 9,000 is still too much, so is it possible for you to reduce this further? So then again you can analyze the program. So for a month or 2 months, and then you can it is possible for him to bring down the length of the program from 9,000 to 8,000, and all this is happening because of his creative skills. Hope people are able to understand.
Yes, sir.
Yes, sir.
That is the reason I'm saying handwritten assembly code, because when a program is writing, there is the creative thoughts and creative skills associated with it. When it is the tool doing it, it is the routine activity. So because tool will not understand in every iteration. Okay. So now I've generated a code of 10,000 line. In the next iteration, if the same input is given, I should reduce the line, number of lines. So it will not understand. So in software engineering terms, so we call it as LOC, lines of code. So it will not understand. That means the creativity is not there. So that is the reason the point it is highlighted here, handwritten assembly code. So just don't laugh at this. So handwritten, there is a meaning. Okay, next. So and so why we say the assembly code has the maximum performance? So because writing the codes and handwritten assembly codes gives you the direct control of 3 optimization tools. So if I'm writing the program using assembly code, it gives you direct control of 3 optimization tools, so which is not available when you're writing the programs using high level programming languages. Okay, so and that you cannot explicitly use by writing a C source code or the source code in any other high-level programming language. So that is the advantage of writing the programs in assembly code. So you get the direct control of 3 optimization tools. Now, what are those 3 optimization tools? So instruction scheduling, register allocation, and conditional execution. Now, all these 3 optimization tools are in your hand. So while writing assembly code, so you can go for scheduling the instruction as you require. That means scheduling the instruction is nothing but you have the flexibility of reordering the instruction in the code sequence. So I don't know whether you people still remember it or not. When I was explaining earlier the concept of pipelining, so 1 or 2 cases we came across the pipelines, and when I was explaining the concept of pipelining, I mentioned there are something called as processor stalls or the processor waits. So especially when the branch instructions enters into the pipeline, so till the branch condition is resolved, whether it is true or false, so we were not letting the next instruction to enter into the pipeline. Yes or no? Do you remember that sequence what I explained to you people earlier?
Yes, sir.
Yeah. So now, so all that thing can be controlled directly by you now. Okay. So say if the branch instructions enters into the pipeline, so then immediately you can go for or executing some useful instruction in that pipeline stall or the pipeline wait cycle. Instead of scheduling it from the fall through instruction or the target instruction, you can go for deciding some instruction within your program which is useful and the execution is required during that stall time, so that useful instruction can be executed. Okay, instead of wasting those cycles. So that is one direct control which you will get. And register allocation. So if I'm writing a program in C or Java, register allocations happen automatically, and that is not under your control. So whatever the compiler or the system allocates the resource, your program the same register it has to use. It is not possible for you to change the register sequence. And even when we're running the higher level program, even we won't be knowing what registers are being used. Okay, and in what sequence the registers are being used. So we just execute our program and our program gives the output and we keep quiet. So but here it is not like that. So you have the complete control of the register allocation. You can decide which registers to use. And so not only the registers, even the stack locations also you can decide. So when you're running a high level programming language, and if you're creating a stack, you won't be knowing where exactly the stack is created inside your memory, and wherever the system creates, that is what we need to accept and we have to proceed with that. But here you have the complete control of defining where the stack should be located inside your memory, and all these things will help you in maximizing the performance of your program. And the third important tool, optimization tool, is the conditional execution. So when you're writing the program in the assembly code, it is possible for you to embed the condition within majority of the instruction. So instead of doing 2 or more instruction, okay, for checking the conditions, now the condition itself can be embedded within an instruction. So you have the instruction also and the condition also within the same instruction, and this again increases the performance of your program. So these are the 3 optimization tools, so which are directly accessible when you're writing the program using the assembly code. And these 3 things are not directly accessible when you're writing the program in the high-level programming languages. So they happen automatically, and this part, these 3 parts, is not under your control. Hope you understood.
Yes, sir.
Okay. We'll stop here. So next is we are going to have a detailed discussion on all these 3 optimization tools. Okay, we'll continue from here in the next class. So let me stop here. And so I got only one S when I asked have you people understood the concept still here. So can I have some more S's or no's? Yes.
Yes, sir.
Okay.
Yes, sir.
Okay.
Yes, sir.
Okay. Thank you. Enough.